All right, let's try to put a lot of these rules together now and kind of synthesize everything, hopefully. So here are some additional properties of roots of polynomial equations. So the first, and that I've mentioned this before, is that if a polynomial equation is of degree n, then if you count multiple roots, like we did here, right? So 2 and 2, it's obviously the same answer, but we count it as 2 roots. Then the equation has n roots. So your degree can tell you how many solutions you should expect. The other thing to note is that if you have a true imaginary solution, then the conjugate is also a solution. So we saw that here. If you have one imaginary solution, then the conjugate is also a solution. So it's just really helpful because if you know some basic information about the polynomial, if you know the degree, like let's say your degree is 3, then you should be expecting 3 solutions. They could be real, they could be imaginary, but you should be expecting 3 solutions. They could be repeats too. If you know that one of your answers is imaginary, there is a second imaginary solution that goes with that. So you kind of have 2 solutions in one there. That makes it a little bit easier. Another thing I want to make a note of here, and we've been doing all this, but just to kind of, again, bring it together, is that when you have an x-intercept, that is also a 0 of the function. So it happens to be a real 0, right? So imaginary zeros don't show on the axis, but real zeros do. So x-intercepts are also zeros. They also relate to factors like we've been seeing. And then you also know that when you plug them in, you get 0. So these concepts are all interchangeable as well. So the fundamental theorem of algebra is obviously extremely important, and it says the following. If a polynomial of degree n, where n is at least 1, or is of degree n, excuse me, then the equation f of x equals 0 has at least one complex root. So we actually end up learning from the fundamental theorem of algebra that every polynomial has exactly n roots instead. And that we actually can completely factor the polynomial if we allow ourselves to include imaginary or complex answers. So what happens here when we have this initial fundamental theorem of algebra, it says that, well, we know that we have at least one root. So what we do is we write the equation like this, so that x minus c1 is our first group, c1 is our root, and then you have some sort of polynomial left over. But what happens is you can apply that fundamental theorem again to q of x. So I can pull out another root from q of x, which is another factor, and then again have another polynomial left over. And what happens is that process continues over and over and over, so that each time we get to a smaller polynomial or lesser degree, we're pulling out another factor. So what you end up with is that every polynomial, like I said, has exactly n roots, and it allows us to factor it completely. So what you're going to see here is that your polynomial can actually be written like this. So we can write it as all the factors. The only thing is that we typically will write the leading term out front. So I know in the past, sometimes when we factor, we have numbers in front of our x's. In this particular form, we do not. It's just x, not 2x or 3x. And then what we do is that leading coefficient comes out front. So that's typically our factored form for polynomials. All right, so let's actually go ahead and do this. So we're going to find a 4th degree polynomial function. And we know that it has real coefficients, -2 and 2, and also the imaginary unit I as zeros. And I also know that f of 3 equals -150. So think of this like a puzzle. We have a 4th degree polynomial. So if I have 4 degrees, my n is 4. So that means I must have n solutions or n roots. And again, I am allowing myself to include repeats here and also imaginary answers, but there are n of them. Now, they gave us 3. So roots, zeros, these are all the same thing. So they gave us 1, 2, and 3. So we're missing 1. I should have 4. I only have 3. But remember, when we have imaginary roots, you also have the conjugate. So if one of the answers is a plus bi, the other answer is a minus bi. Now here I don't have the a part, but it works the same way. If one of the answers is just bi, then negative bi is another answer. So if I know that I is a 0, then negative I is also a 0. So I do have my 4 solutions, right? My 4 roots are 2, negative 2, I, and negative I. Now we write our factors like this. It's always x minus c. In our roots, that's your c values. So what this is going to look like is going to be x minus 2, x minus negative 2, x minus I, and x minus negative I. Now you are going to clean this up and we'll rewrite it. But we're missing one thing. So in your formula, let me find it here. You do need a leading coefficient, which matches with this one here. So here I don't know my leading coefficient. I'm just going to call it AN for now. But I do have all my factors. So how am I going to figure out my leading coefficient? Well, there's one last piece of information I haven't used. I know that f of 3 is negative 150. So what I can do is I can plug in 3 for x. And I know when I plug in 3, my answer is going to be negative 150. So now I can go ahead and I can solve. So let's simplify this. All right. 3 minus 2 is 1. 3 plus 2 is 5. Now here, if you have imaginary numbers, you're going to have to multiply that part out. So 3 times 3 is 9. 3 plus positive I is going to be just 3i. Here you're going to get minus 3i, and then on the end you'll get negative I squared. This becomes a 5. And now when you multiply out, because they're conjugates, that middle term is going to cancel. Negative I squared is negative 1. So you have AN times 5. Here, this becomes 9 plus 1, which is 10. So your problem becomes, let's see, 5 times 10 is 50. So 50 AN is equal to negative 150. And when I solve this, I get AN is equal to negative 3. So finally, I can put it all back together. All right, so let's put it all back together. I'm running out of room here. Let's go, I'll just do it right here. All right, so I have f of x is equal, my leading coefficient is negative 3, x minus 2, x plus 2, x minus I, x plus I. Now, this is what we call factored form, right? It's using this linear factorization theorem on the page before. So this is our factored form, but you want to be careful here. Sometimes the homework may ask for in the factored form, and this would be perfectly acceptable. But if it doesn't say factored form is fine, then you really should multiply this out. So they are looking for a 4th degree polynomial, which means that they actually want the final answer. So you're going to have to actually multiply this all out. The nice thing is, though, is that multiplication is commutative and associative, so you can kind of group as you want. I recommend grouping complex numbers together that are going to cancel and then grouping real stuff together. And you can only multiply 2 things at a time. So here I have x squared plus 2x minus 2x minus 4. Here I would have x squared plus ix minus ix minus I squared. If I keep simplifying, this cancels out. I have x squared minus 4. This also cancels out. And remember that I squared is negative 1. So I have negative 3 times x squared minus 4 times x squared plus 1. So I'm getting there. I still have to keep multiplying everything out. So I'll multiply through by the 3 first, and I have negative 3x squared plus 12. And then finally, I can multiply by the last term. Again, I don't have a shortcut here. You can only multiply 2 at a time. So we're going to multiply this next group out. Let's see, maybe I should just do it on the back real quick. So let's see. I should have left myself some more room. All right, so here I'm going to get negative 3x to the 4th, right? Square and square is going to be 4, minus 3x squared plus 12x squared plus 12. Combining my like terms, I have 9x squared plus 12. So my answer here in just the regular polynomial form, not in that factored form, is going to be negative 3x to the 4th plus 9x squared plus 12. And notice here that we asked for a 4th degree polynomial at the beginning of the problem, and we have a 4th degree polynomial. I do encourage you, again, to kind of take your time here, maybe pause the video and go back and see if you can do the problem on your own or read through it again so that you're understanding all the steps. What I did here to start is to just note that my degree was 4. So I was looking for 4 solutions or roots or zeros. I had 3, but I do actually have 4 because when we have imaginary units or imaginary numbers, the conjugate is also a solution. So I was able to find my 4 solutions right away and write them as factors. Then I plugged in 3 in order and set it equal to negative 150 in order to find that leading coefficient. And then I had to multiply everything out. So a lot of basic algebra here at the end was just multiplying out and taking our time. All right, the last thing I want to talk to you guys about is Descartes' rule of signs. And Descartes is a famous mathematician. He's done quite a bit in mathematics. I won't even start in the video, but he's everywhere. So this is one of his rules. So Descartes' rule of signs helps to determine the number of positive and negative real zeros of a polynomial function. So remember before when we had our options of possible rational zeros, we had all these positive ones, all these negative ones. So Descartes' rule of sign allows us to narrow down to how many positive and how many negative we should expect. It's still a little bit tough to use. Sometimes it's not a straightforward answer, but it does help us to narrow it down. So let f of x be a polynomial function with real coefficients and a non-zero constant term. And the key here is that your terms are in descending powers. So just like for most of our things, we like to have our polynomials with those decreasing or descending powers. So what it says is the following: the number of positive real zeros either equals the number of variations in sign or is less than the number of variations by a positive even integer. Now, what are variations? A variation in sign is a change from positive to negative or negative to positive in successive terms. Okay, so for instance, let's say I had something like f of x equals 3x squared minus x plus 1. Okay, so here I'm starting from positive to negative. So this is one change. And then I'm going from negative back to positive. So this is a second change. So this has 2 changes in sign. Here, I'm starting at positive and I'm staying positive, so there's no change. And then I'm going from positive to negative here. So there is only 1 sign change here. So that's what we're talking about by variation in signs. We're looking for how many times does that sign change. The number of negative real zeros either equals the number of variations in sign occurring in the coefficients of f of negative x, or is less than the number of variations by a positive even integer. So let's see if we can apply this to an example here. So here is our function, f of x equals x cubed plus 2x squared plus 5x plus 4. So notice that I start positive, I stay positive, I stay positive, I stay positive. So here there is no sign change. So the number of variations is actually 0. If you start and stay with the same sign, then your variations are 0. So the number of positive real zeros equals the number of variations of f of x, or is less than the number of variations by a positive even integer. So our number of variations in this case happens to be 0. So the number of positive real zeros is either equal to 0 or it's less than this. Well, it doesn't make sense for the number of zeros to be less than 0, to have negative zeros. Not a negative answer, but like the concept of having less than 0 answers. So here, if your variations is 0, then that's just going to be the answer. So the number of positive real zeros here happens to be just 0. So now if you were checking your answers, right? Let's say you had all those possible rationals, anything positive, you know, in this case would not work. The number of negative real zeros is equal to the number of variations of f of negative x, or is less than the number of variations by a positive even integer. So for this one here, you have to plug in negative x. So this is positive. So I go to my function here. I'm going to replace all the x's with negative x. And then I simplify. So I have negative x cubed. Here, the negative will cancel with the square, so it's just 2x squared. Here I have minus 5x plus 4. So if I think about my variations, I start negative and then I change to positive. So that's one change. Now I go from positive to negative. That's another change. And now I go from negative to positive. That's another change. So you have 3 variations here, right? Because I go from negative to positive, positive to negative, and then back to positive. So it's changed 3 times since the start of the problem. So the number of negative real zeros is either the number of variations, which is 3, or is less than this by a positive even integer. Positive even integers are 2, 4, 6, etc. So we're counting down by 2s. So 2 less than this would be 1. I can't go any smaller because then I get into negative territory. It needs to be positive here. So the number of negative real zeros in this case would either be 3 or 1. Let's just say 1. Sorry, guys. That's a 1. So there are either 3 or 1 negative real zeros here. Again, it's not a perfect answer, but at least it kind of narrows things down for us. So we know that there are no positive real zeros, and there could either be 1 or 3 negative real zeros. So it just helps to narrow down. So when we're listing the possible rational zeros, because we always have all those plus or minuses, it at least helps us to narrow down. So in this case, I know I don't have to check my positive values. They're not going to work. I would have to check my negative values though, and I would expect either 1 to work or up to 3 to work. And then at this point, you could do the graphing. Look at your graph to see if you have any x-intercepts that you can see. You could also use synthetic division here to see if we can find which roots are working there as well. So it's another tool to help us narrow down what our possible roots could be so that we're not testing as many things. So it's a nice tool here. And again, for me, my favorite tool for this is probably to graph and use those x-intercepts to see if there are any real solutions first. And that kind of helps to narrow it down as well.